Hi, physics. Mr. Chernowski here. This is Chapter 13, Homework 3, Problem 1. So the ISS, the International Space Station, orbits 4.00 times 10 to the fifth meters above the surface of the Earth. So part A, how far is the ISS from the center of the Earth? Okay, so red pen, step, what are we looking for? How far is the ISS? Let's call it D for distance. D is equal to question mark meters. Okay, so how are we going to do this? Just a simple sketch. So what we're saying is the ISS is this far above the surface of the Earth. Okay. So if that's the Earth, the ISS, this is me drawing a little satellite here. What I'm saying is this distance is 4.00 times 10 to the fifth meters. So how far is the ISS from the center of the Earth? Well, it's that distance plus the radius of the Earth. So this is not to scale here. So let's call this first one the height. It's the height above the surface. Radius of the Earth is, check our little table down here, 6.38 times 10 to the 6 meters. All right, so you can just do this in the calculator. Another way of looking at this is 4.00 times 10 to the fifth meters is the same thing as 0.400 times 10 to the 6 meters. See what I did with the exponents there? So 6.38 times 10 to the 6 plus 0.40 times 10 to the 6. The distance you're going to get, so distance is h plus radius of the Earth, is going to end up being 6.78 times 10 to the 6 meters. So there's our answer for that one. Now for part B, what is the orbital period of the ISS in seconds? Okay, so that was A right there. For B, what are we looking for? We're looking for T is our symbol for orbital period. Remember, orbital period is a time. It's how long it takes the ISS to go around. So T is equal to question mark seconds. And then for the last part, it's going to be what is that time, but in units of minutes. So that'll be a field goal post thing when we get to it. All right, so how can we get T? We're going to use Newton's version. We're going to use the pretty version of Newton's version of Kepler's third law. So this one here. You can also do this one. Okay, now notice this one is already in terms of T. So in a sense, this one's more direct, but this one's a little trickier to do in the calculator because you've got to take something to the 3/2 power and you've got to have something in a square root in the denominator. So if you're comfortable doing it with, this one here, the one I put in the box, go ahead. But I kind of recommend, at least when you're starting out with these problems, use the pretty version. So T squared is equal to 4 pi squared. And I'm going to put the R up here. This was confusing some people in class today. Compare what I just wrote to what I have here with the R to the R cubed hanging off the end. It's still in the numerator. It's going to be multiplied by the 4 pi by the 4 pi squared. So it doesn't matter where you put it. So that's what we've got. So we've got to put in our numbers. So 4 pi squared. R. Okay, well, the R, that's the R we're going to use. That was our answer for part A. So 4 pi squared times 6.78 times 10 to the 6 meters. And only that last thing is going to get cubed. And all of this divided by big G, which is 6.67 times 10 to the minus 11th. And forget about the units for that one. And m is the mass of the thing being orbited, which is the Earth. So what's the mass of the Earth? It's this number right here. So 5.97 times 10 to the 24th kilograms. Okay. So here's what we've got. If we do this, and these numbers are in the right places. If we do this correctly, this will get us to t squared. Now, it's a little tricky to do this correctly. So a couple different ways to do it. One way to do it, once you've done enough of these, you would do this entire thing all in one big shot and just hit enter once at the end, and you would have the right number. Another way to do this is, let me show you. You could put big parentheses around the bottom. There's an order of operations thing that you've got to get right here. If you're not careful, you would end up doing the numerator correctly, dividing by 6.67 times 10 to the minus 11th, but then multiplying by 5.97 times 10 to the 24th. So you've got to be a little bit careful about that. So one way to get around that would be to use the big parentheses at the bottom. Still another way would be do the whole numerator, get an answer, do the whole denominator, get an answer, and then divide the numerator by the denominator. So that's the way I'll actually do it here. So if I ask my calculator, 4 times, I would learn to use the pi button on your calculator. You can just put in 3.14. That'll get you close enough. There's rounding in these things anyway. But I would learn to use the pi button. It'll save you a little bit of time. Remember to square it. So 4 times pi squared times 6.78 EE6, and I need to cube that. Okay, so your calculator, mine doesn't have a cubed button. Your calculator likely doesn't either. You need to find a button that will take the thing to the cubed, to the power that you want. So on my calculator, there's a button that looks like this, X to the box. So that means, when you hit that button, it takes the thing to that power. So you can do that. On another calculator, it might be a caret, meaning like exponent up there. So it's going to depend on your calculator. But anyhow, I'm hitting the X to the box button. I'm hitting 3. And when I do all this, I get this enormous number. 1.23, I'll keep some extra digits here. 04, yada, 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 times 10 to the 22nd. And I'm not even worried about the units because the units aren't even going to matter at this point. And then for the bottom, 6.67 EE minus 11 times 5.97 EE 24. When you do that, you get 3.98 199, I'm going to call it 20, times 10 to the 14th. All right, so now I've got to do that. 1.2304 EE22 divided by 3.982 EE14. Hit enter, and I get a number that looks like this. My calculator opted not to give this to me in scientific notation. 3089904.5.71. So is this my answer? Well, no. Look at our chain of equal signs back here. This leads all the way back to t squared. So this is, the units for that would actually be second squared. That's t squared, but I don't want t squared. I want t. So I need to take this to, I need to get the square root of this. So the way I do this, your calculator does have a square root button. You could use that. I'm going to use this button again, and I'm going to take it to the 1/2 power. Taking something to the 1/2 power is equivalent to taking the square root of it. So I'm hitting X to the box. You could write 1 divided by 2, or you could write 0.5. If you do all that, you end up with 58.7. So let's call it 55. I'll round off here. 60. This is equal to t. And what units does this have? This will have units of seconds. So there's my answer for part B. Now remember, part C is what is the orbital period of the ISS in minutes? So what formula do I use? I'm not actually using a formula. I'm going to be using field goalposts, because 5,560 seconds, I don't have a good feel for, that amount of time. I don't usually talk about times in thousands of seconds. So let me turn this into minutes so I get a sense of what this is. So T is equal to 5,560 seconds. All right, so I need field goal posts that will get me out of seconds and into minutes. So what will that look like? Well, I'm starting with seconds on the top, so I need to have seconds on the bottom, minutes on the top. How do they relate to each other? 1 minute is the same thing as 60 seconds. So if I do this, seconds goes away, you end up with something in units of minutes. So take your last answer, divide it by 60, and I have 92.6448501 whatever. So let's just call this 92.6 minutes. Okay. I know what 92.6 minutes is. That's a little bit more than an hour and a half. So I'd rather, sometimes I'd rather talk about the time like that. So there you go. That was Newton's, well, first of all, it was a sketch. Hopefully, if you see the sketch, make the sketch on paper. But if you don't make it on paper, at least have it in your brain. Hopefully, you can see what's going on there and why we got our answer for part A. After that, it was Newton's version of Kepler's, the pretty version of Newton's version of Kepler's third law of orbital motion. And then after that, it was field goal posts. So hopefully you found that helpful.